Okay, so we talked last lesson about electronegativity. And now we're going to look at that scale. So really you've looked at electronegativity conceptually. You've maybe looked at a few numbers. So this scale was created about 80-something years ago by Linus Pauling, a famous chemist. He assigned numerical values for the electronegativities of the elements. He maxed out at 4. There might be a reason why he chose 4, but it's sort of arbitrary. It's setting fluorine equal to 4 as it is the most electronegative, and francium at about, I think, 1.1 because it's the least electronegative. So here, oh, it was on the next slide. I was wrong, 0.7 for francium. So we know that electronegativity gets larger as we move across the periodic table. So let's go back to our understanding of periodic trends. Electronegativity goes up. Well, let's go back to electrostatics. Coulomb's law. More charge, more force. Closer together, more force. So as we move from left to right, the distance, we really care about only the distance and the charge. Distance is approximately the same, but protons increase, so charge increases. So the force goes up because the number of protons increases and the distance is approximately the same. Well, if I look going up, here the effective nuclear charge is the same. So the force felt by the valence electrons from the nucleus is about the same, but here distance increases going down. So that means the force decreases going down, which means less electronegativity. So really you can look at it in terms of just distance from the nucleus and the effective nuclear charge. As it gets further away, the nucleus can't pull valence electrons as tightly, which is why hydrogen has a much higher electronegativity than francium, because francium is a much larger atom. As you go across, let's say the second row from lithium to fluorine, lithium does not have a lot of protons in its nucleus. Fluorine has a lot more, so it can pull a lot more tightly on its valence electrons. Okay. By determining the numerical difference between electronegativities in the bond, you can compare polarities. So what we're looking to do here is, this is a fancy way of saying difference in electronegativities. Going to use the delta. So greater change in electronegativity, more polar, until you get to ionic. And numerical differences can help predict the type of bonds that will form. So let's just say we have none here to huge here. And we'll do small and large. So if I have no difference in electronegativity, I know this is nonpolar, covalent. If I have a huge difference, then I know this is ionic. Anything in between here is what we say a continuum. So we have polar here in the middle and increasing polarity as we go across. So atoms that have a very small difference in electronegativity might be slightly might make a molecule that's slightly polar or a bond that's slightly polar. But as we go across, it becomes more and more polar in terms of the difference in electronegativity between the two. You'll find books that say the dividing line between polar covalent and ionic bonding is 2.1. Well, you can find plenty of examples on the periodic table where the electronegativity is less than 2.1, but it is an ionic bond. So for us, we're going to stick with the idea of metals and nonmetals defining an ionic bond. Also, books will say 0.5 is the difference in electronegativity that defines polarity. Well, just be careful with that because it's not a hard and fast number. It's a continuum. So anything on that continuum you can describe. but in this class, it'll be very specific. You'll know if it's polar or nonpolar because we'll practice with it a lot. Okay, so how can electronegativity be used to compare bonds is a question we were studying today. So electronegativity measures how strongly an atom will attract shared electrons. We've talked about this a couple of times. The greater the difference, the more polar the bond will be. And in ionic bonding, they're so different that one of the atoms actually steals the electrons of the other. So it's completely transferred. Okay.